Good afternoon. Thank you for joining us for Intro to Ammonia Refrigeration webinar. My name is Beth and I'll be hosting today's webinar. We'd like to start today with a safety moment. Safety is a core value at PGE and we want to remind you to be safe around electricity. As you consider installing or retrofitting new equipment, please keep safety in mind. We also encourage your family and staff to be prepared with an outage kit. You can visit our website for more safety information. We also want to thank the Energy Trust of Oregon and the Northwest Energy Efficiency Alliance for their support in co-sponsoring this series of free energy efficiency trainings that are open to all Northwest utilities and their customers. Before I introduce today's presenter, I'd like to show you some tools you'll be using during the webinar. We have a chat window to the right, and at the end of this webinar, there will be a polling window which will appear at the bottom. If you have any questions during the webinar, you can submit them to me through chat, the host, and the instructor will answer them at the end of the webinar. And because today is an informal session, if you'd like to share an example or you have a question you'd like the instructor to address immediately, we'd like to encourage you to raise your hand using the raise hand icon, which you'll see. We'd like to encourage you to chat with me that you would like to ask a question of the presenter live, and we can unmute you and you can ask the instructor a question. At the top left corner of your screen, underneath the Quick Start menu, which I'll highlight here with a red highlighter, you'll see several tools, an arrow, a text tool, and a marker. The presenter will ask you to use these annotating tools on specific slides during the webinar. And now I'd like to introduce today's presenter. David Wiley is Vice President of ASW Engineering and Management Consultants. David was one of the founders of ASW in 1976. He has an engineering degree from Cal Poly San Luis Obispo and completed an MBA at National University, which has provided him with even more tools to analyze energy efficiency investment from both a mechanical and a financial perspective. He holds college teaching credentials and has an ability to take sophisticated engineering concepts and relate them in a way that you can understand. Several of his articles have been published in trade magazines, and he has written a book titled New Refrigerants for Air Conditioning and Refrigeration Systems. David recently served as the committee chair for ASHRAE Custom Engineered Refrigeration Systems Research. And now I would like to hand the presentation over to David.
Thank you, Beth, and I hope all can hear okay, and welcome to our introduction to industrial refrigeration. So as you can see in the agenda here, and we've got just a little bit under an hour, we want to take a look at a very successful refrigerated warehouse that accomplished a LEED rating, LEED Gold rating, and more so it's what some of the technologies that they applied. And then let's take a closer look at those technologies, primarily floating head and floating suction pressure. These are actively controlling the suction and discharge off of a compressor, and we find substantial savings available from those control strategies. And then the third bullet here, potential energy savings by utilizing variable frequency drive on a screw compressor. Those are some interesting results, and we have some actual measured data to take a look at. So that's what we have in store for you today. And first, let's take a look at this super efficient refrigerated warehouse. Here's a pretty good photograph of the outside in the bottom left corner there. It's about 135,000 square feet, and compared to a standard refrigerated warehouse only using about 40% of the energy, so that's 60% savings, about 3.5 million kilowatt hours a year. From the outside, it looks like maybe any other warehouse, but when you take a look inside, the picture on the right, you can see the very tall nature of the building. The aspect ratio of this facility is able to fit about 4 times the amount of product as you would in a typical warehouse. You know, being tall like this, it also gives a lot of volume of area relative to the square footage. So we can see the height of the storage area, and this is a retrieval system. It's not automated. A person actually would direct the carriage here to the product on the shelves. However, the high area or the height of this area provides a lot of storage for the square footage itself. These are about 50-foot high racks, and these special lifts are used to retrieve the product. We can also, in this picture, see the lighting. This is LED lighting, which is about 80% less than energy use than high-intensity discharge lighting, which might have normally been used, as well as being on occupancy sensors. And the LED lighting, which in some cases uses almost as much energy as the compressors, would be off when there isn't any occupancy in a specific area. So on this next slide here, we can see the refrigeration system that's supporting that particular warehouse. And from the initial view here, we have there are 4 penthouses with evaporator coils in it, and the suction lines coming back to 3 235 horsepower compressors. These do have variable speed drives on it with volume index, so efficient compressors. The hot gas goes off to an efficient condensing unit, employing floating head pressure control with variable frequency drives on these fans. We also have variable speed on the evaporator fans, and we'll be taking a closer look at all of those aspects of it. Here's a picture of the compressors. So this is a variable frequency drive portion on the compressor right here. There's also slide valve. We'll do a little comparison later on between slide valve control and variable speed. Next slide here is looking at the back of the house, where we have the evap condensers. Here's a surge tank for accidental release of ammonia, could actually be absorbed into that tank. Here's a look at the top of the building. These are the penthouses where the evaporator coils reside. There's 4 of them. 1, 2, 3, and the 4th one's right. You see just a little bit of it there. So the air handling unit is accessible through the door on the top of the building. Sometimes that's a nice advantage compared to being suspended from the ceiling inside. And you obviously can see the photovoltaic panel on the roof here, which delivers a little over a megawatt of power at peak time, which also is about 70% of the facility's energy use is delivered through the photovoltaic system. So compared to standard practice, we've got a lot of the efficiency aspects built into this warehouse, and as such achieve the gold rating from the LEED certification program. So when we compare the warehouse we were just looking at, which might be this very efficient example, versus in this chart, we have in the back here, we'll say this is the 1985 vintage. So if this typical warehouse was built prior to 1985 with standard practice in choice of machinery and controls, it would typically use about 3.5 million kilowatt hours per year. And then notice the second example here is, what happened over a 20-year period. Standard practice in 2005. And if we look at the individual components here, evaporator fans, compressor, lighting, medium temp compressor and condenser, you can see where efficiency gains might have occurred. A little more efficient motors on the compressors is represented right there. Here the lighting went from HID to fluorescent, some form of fluorescent, a little more efficient motors on the compressors. But then if we go to 2008, what we'll refer to as energy efficient, of course, here you can see the big step in evaporator fan energy reduction, and that's by the utilization of variable speed drives on evaporator fans. So when the load is not necessarily at its peak in the process or the refrigerated warehouse, we can see what results. Pretty substantial energy savings there. Continued improvement in the compressors. And then in the 2012 most efficient, we've got a continued improvement in fan motor efficiency, permanent magnet brushless DC motors. We've added variable speed to the low temperature compressors. Lighting has gone to LED lighting, and a continued improvement on the condenser fans. So a most efficient warehouse today would achieve the same amount of cooling for about a third of the energy, so going from over 3 million kilowatt hours to just a little over 1 million, and that's achievable with today's technology. And what we'd like to do is continue some presentation of how that might be done. So most refrigeration systems will be categorized by one of these three groups here. We have small single systems, generally up to about 75 horsepower, sometimes ordered from a catalog. Let's take a look at one of these. Here we go. So the condensing unit, compressor, we're looking at the outdoor unit here, and the refrigerant piping would go to the evaporator inside the storage area here. So we've got three individual units. These are typically ordered from the catalog, not necessarily the most efficient, as a result only used up to maybe a 50,000 square foot facility. Good news is they're readily available, prepackaged, fairly easy to service. On the other hand, fairly short life, not being efficient, and generally you don't see ammonia used in systems like this, although with the advent of the micro-channel condenser, that would be a casted aluminum condenser, we just may see some smaller ammonia systems showing up in some of our warehouses. The next category, intermediate packages, generally range from 50 to 500 horsepower. Let's take a look at one of those. Are typically a pre-constructed system. You can see the skid mounting here, the compressor lineup, the controls cabinet and associated piping and vessels. Quite often these are halocarbon refrigerants as compared to ammonia. Often we'll have more efficiency embedded into this system than you might find from a cataloged or single system. Take a little more skilled maintenance to take care of it, and also generally not easy to expand, since the piping and electrical is all skid mounted here. It would not easily facilitate adding on, say, more capacity in another compressor. If we look at the large built-up systems, and these are usually custom at each site. So here we see compressors as an individual pad-mounted piece of equipment with piping and vessels. These are usually built up at the site. Unlimited tonnage, we can usually add more to these systems relatively easy. We can see a smaller compressor here up to some larger ones, so adding on or staging equipment is usually easily accommodated. We usually get long life here, 20, 30 years, sometimes longer, and also often our highest opportunity for efficiency. This does take a while to build, so you're not going to order all of this out of a catalog. It's custom made. It's usually our higher first cost, and typically these are ammonia systems, although in some newer systems we're finding carbon dioxide as an alternative refrigerant. So we have large, medium, and small. So we thought for those of you who are listening in here, if you could grab your arrow pointer up in the top left corner and just click on the size system that you're particularly interested in here. I think you can get your name. Let's see, I'll try to do, there we go. Thanks, Tom. So in the larger systems category, anyone else want to respond there? We've got a few others online. And that helps just to focus our discussion through the rest of the talk here. Okay, some medium size. Give it another second or two here, and then we'll just keep moving along.
Hey, David, I just wanted, sorry, this is Beth. I just wanted to interrupt and say that the arrows that David is talking about are up here. I'm pointing to an arrow right now. If you click on that, you can select something and say what type of unit you have. Thank you.
Okay, thank you, Beth. Good. We're going to have another little pointing exercise in a few more pages, so glad you got a hold of that tool. Okay, so scooting along then, and since we're going to be looking more at the large built-up systems, we'll focus there, although many of the principles that we're going to cover here work even on the smaller systems. They just generally don't come included from the catalog. And in our larger systems, we usually see the screw compressors looking something along these lines. Okay, so to have a discussion on refrigeration, we've got our proverbial drawing here where we discharge gas out of the compressor, getting the refrigerant hotter than the ambient. You know, it could be a 100-degree day. Well, then our refrigerant might have to be 130 degrees to get the heat out of the refrigerant, and the resultant condensing or going from vapor to liquid occurs. We would call this the liquid line. There has to be some sort of a metering device that regulates the flow of this liquid refrigerant into the evaporator at a rate that's equal to that refrigerant evaporating or phase changing. We don't want to feed surplus liquid back to the compressor. We want to keep the liquid in the evaporator for the most part until it's utilized. Some of the bigger systems do have a pumped liquid overfeed type of application where instead of a metering device here, we have a pump and then a flow control device at the evaporator. But in either case, we're trying to get the evaporating done and get the cooling effect as a result of the refrigerant being at the lower pressure, which the compressor maintains by pulling the vapor out of the evaporator. As the refrigerant enters in here, then the phase change going from liquid to vapor absorbs the heat, drawing heat out of the space, and we can control the temperature of this evaporator by whatever pressure the compressor would provide. The colder we want to go, the lower the pressure. If we're considering ammonia as a refrigerant, for example, if we want to keep this evaporator at about positive or plus 20 degrees Fahrenheit, we would maintain a pressure in here of around 4 pounds per square inch, pretty near atmospheric pressure or gauge pressure of 0. If we wanted to get to minus 20 degrees, we would need this evaporator to be in a vacuum, approximately 34 inches of mercury as a vacuum. That's often done, although when we operate the low side of the system in a vacuum, we run the risk of any leaks allowing air to be entrained into the refrigerant. Of course, air is generally considered a non-condensable, mostly being nitrogen, so most of that would end up here in the condenser and needs to be bled off periodically. Of course, an excessive leak would end up in compromising the system. As air gets in the condenser, it causes the pressure in the condenser to go up, effectively making the condenser smaller. So ammonia is a great refrigerant, but when we start getting below 20 degrees, and we do run into vacuum issues for that. So we were just looking there at the low end, being, say, minus 20 degrees evaporating temperature, and then, of course, condensing or getting rid of the heat, 95 to 100 degrees. And this first column here on the graphic is showing our typical condensing temperature and evaporating temperature of a low temperature system. So trying to maintain the minus 20 and a plus 95 to 100, this is known as lift, or the ability to maintain these two separate pressures. This is what the compressor would see, and it relates to the compressor or compression ratio. If we have a milder day, as in the second column here, notice that we might condense at a lower temperature, say 75 degrees. It might be 55 or 60 degrees outside. And if that's the case, if we were to reset our controls and allow the condensing to take place at this lower temperature, that would reduce the compression ratio. This is what we're referring to as floating the head pressure, or adjusting the discharge pressure relative to the ambient. There's also an opportunity to float the suction pressure. So say it isn't the hottest day, and we don't need minus 20 to maintain product temperature. Say we could do that at minus 15 degrees, then that 5 degrees of reset, or raising the suction temperature and pressure, will provide a reduced compression ratio as well. A general rule of thumb here is for every degree we can bring the suction temperature up, there's about 2% energy savings. It would also apply to the head pressure. For every degree that we can bring the condensing temperature down, there's roughly 2% energy savings at the compressor. Thus, whenever we can reduce the head pressure or raise the suction pressure, the resultant compression ratio reduction gives us some excellent energy savings. We can see in a higher temperature system, or maybe we're at 20 degrees suction, the same thing applies. We can float the head pressure down, raise the suction pressure up, and it actually looks like a larger percentage. It's roughly the same kilowatt hour savings, but as of the overall energy consumed, this floating head pressure here may represent 30% energy savings, but for the low temperature system, it might only represent 20% because of the added energy for the lower temperatures. So we have graphically portrayed here the concept of floating head, floating suction pressure, and that would be an active control. The next couple of slides will show us a different way of looking at it. If we say in the middle of summer, on a hot summer day, we really can't take advantage of Mother Nature being down in the 50s, so our condensing temperature is just going to be whatever it ends up doing. Likely on a day like this, where the ambient is 70, 80, 90 degrees, all the condensing fans are on, and we're doing the best we can to maintain as low a pressure as we can. All systems full bore, you might say. But look out here in the wintertime when the ambient or wet bulb, dry bulb temperatures are down in the 40s and 50s. We could be condensing down at a lower temperature. However, if our controls are set for a fixed condensing temperature, then this is a lost opportunity to save energy. Most of the floating head pressure savings occur during the mild weather. So if we were to look at the concept of floating then, on this next slide, notice when it's a 50-degree ambient, maybe we could condense at 65 instead of 85. Something like that would represent a substantial energy savings. And so it's generally in the winter that we are able to take advantage of this. I know that's not when the highest load is here, but these are valid and achievable energy savings. And in order to get that floating head pressure control, the system might look something like this, where we measure the ambient temperature, and the controller then would look at the refrigerant pressure, consider how close the refrigerant can be to the ambient in terms of temperature, and then just a set point for the fan speed to achieve a pressure that condensing unit can attain on a particular day. This is a form of active control, so as the ambient temperature goes up, our set point would change. What we don't want to have happen is a set point that's so low that all the fans end up at full speed trying to attain a condensing temperature that the system can't achieve. In other words, we don't want to set it too low. There's a trade-off here. We're going to be using fan power to get the lower condensing temperature, but that's going to render savings at the compressor. So we just want to be sure that we have more savings at the compressor than we expend at the condenser. At some point, we'll have a sweet spot there where we're achieving the greatest savings at the compressor that we could, and yet slowing the fan down to a set point that's attainable based on the ambient. A control system of that nature looks something like this. So here's a control panel for variable speed condenser control. These are variable frequency drives. This control panel generally assembled on an existing facility without floating head pressure control. It's assembled and then brought to the site. There's a microprocessor for controlling communications, variable speed drives, and I think in this case here, each condenser fan had its own variable frequency drive. It is possible to put several fans on one drive, but at the same time, individual fan speed control may be desirable. We may ask, why wouldn't somebody have floating head pressure control? And there might be some concerns here. I'm going to go back to this slide here. Quite often, the condensing pressure is fixed at a higher pressure in order to avoid any vapor from forming in this liquid line on the way to the evaporator or on the way to the metering device. And one way to keep that vapor from forming is to maintain a higher pressure. So if that would be the case, if we are avoiding flash gas, as it's called, by means of setting a higher pressure, we generally would consider a form of liquid subcooling to avoid that. Sometimes higher pressures are desired to maintain a steady flow of liquid from the system to avoid erratic operation. And it's a high energy price to pay for something that should be controlled by another means than just having excessively high head pressure. There are times when hot gas is taken off of the compressor discharge and used to defrost an evaporator. So during those periods, it's often resetting the controls to maintain the higher temperature and pressure during the defrost cycle, and then when defrost is terminated, back to floating head pressure control. So defrost is a valid reason to have higher pressure. And then one other concern that often comes up about floating head pressure, if we had a screw compressor here, and I know the picture kind of resembles a reciprocating compressor. Well, with the screw compressor, there's an oil separator because of the oil that's injected right into the rotors. And some systems required a higher pressure and associated velocity of refrigerant to separate that oil. Systems that are designed for greater efficiency and floating head pressure would have an oil separator that could do that at much lower pressures and such achieve the floating head pressure. So sometimes there's a limitation that's in place due to the selection of equipment. Some of the equipment that was maybe purchased in the 80s, maybe 90s, where energy efficiency wasn't quite as pronounced or desired as today, would unfortunately end up with a design that does not easily accommodate floating head pressure, and as such, new equipment might be considered, especially when considering the opportunity here. If we move along past the control panel to a typical day in the life, or I should say 2 days in the life of floating head pressure control here. So notice we've got the ambient temperature down at 50, and in this example, our condensing temperature set point, which essentially sets the fan speed of the condenser. In this example, we're showing that at 70 degrees Fahrenheit. That's because of the low limit that this compressor would have for its oil separation. So even though we might have a condensing set point of 60 degrees, we're going to say our low limit here will be 70 degree condensing, and that's due to a compressor limitation. So as the day gets up to 60, 65 degrees, notice the set point changes, and we have about a 10 degree approach here to the ambient. So as the ambient goes up, the set point goes up, thus controlling fan speed to an achievable level. And as the ambient goes back down, notice the set point goes down to the low limit, maintaining that. The next day is an example of a little warmer day, and notice the ambient temperature going up above 80, and up goes the set point until we hit the high limit. And the high limit is that situation where all the fans are running at full speed. So a actual condensing temperature would be whatever is attainable on that day. Here it says high limit of 90, but the actual condensing temperature would be higher. So if you grab your arrow, and let's say we're here on the ambient temperature being about, it looks like 87 degrees or so. If this was the ambient, put the arrow where you think the actual condensing temperature would be. And here's a hint. It's above the high limit. Let's say this condenser has about a 10 degree approach. There we go. Perfect, Tom. Like that. Yeah, so we're not exactly sure where it would be. It depends on the system limitation. So if we're at 85 degrees, then yep, we might expect something near 100 to occur. And if all the fans are running at 100% speed, 60 hertz, that's what we might expect. I know some systems are actually incorporating a bypass in the variable frequency drive, such that if we know we're going to be operating at this condition for any length of time, they actually will switch the variable frequency drive out of the fan circuit and just run it across the line at 60 hertz, really saving the drive for a milder day. Okay, well, thanks for responding to that. So back to our chart here. We've just been looking at the floating head pressure. Let's take a second to look at floating suction pressure on the other end of the system. So what we're saying here is, how cold does this evaporator need to go? And generally, that temperature is dictated by the product or the process that we're running. Now, there may be times when it's not the hottest day or not so much product coming and going out of a warehouse that we could actually set this temperature and pressure up to a higher set point and still keep the product at a desired temperature. Sometimes we will call that the floating suction pressure. There's two areas that we use for this temperature adjustment. So one would be the fan itself. So as we get down to the set point, we might slow this fan down, thus saving energy at the fan. And of course, any kilowatt hours expended on this fan motor ends up as heat in the refrigerated space. So if we can slow this fan down and still maintain product temperature, of course, the air has to be thrown across the evaporator and out into the refrigerated space sufficiently to keep the product at temperature. But first approach would be to slow the fan down, and then the second approach would be to raise the suction pressure up, thus reducing the compression ratio or lift on the compressor. If we take a closer look at a typical evaporator, and we're talking about these fans and the motor behind it, so refrigerant being fed into the coil and air being drawn in over the coils and thrown out into the refrigerated space. Quite often the fan speed here would be reduced down to about 70% of full speed, thus still attaining adequate throw. And the savings at 70% speed are actually pretty phenomenal. Here's our typical fan power curve, and since there's no duct work on these evaporators to speak of, we get pretty near the results as shown by this typical graph. So if we go to 70% fan speed, we can see maybe only using 30% of the energy. So, for example, if you would take your pointer, grab your pointer. If we could slow the fans down to 50% fan speed, where are we going to be over here on the fan power? Stick your pointer over here. Yeah, there we go. So, can we go down to 50% speed and still get adequate circulation? And in some cases, that's kind of asking a little too much. In other cases, it seems like we get adequate throw, and have seen situations where the pallets are lined up in such a way that it increases the air circulation rather than blocking it. But in a lot of applications, 70% speed is maybe the lowest speed you would consider, and that gets substantial energy savings. What does a variable speed control panel look like? Well, it looks a lot like the condenser control panel. Variable frequency drives, microprocessor for control. So we get the fan speed control out of it. And here's what a day in the life of a floating suction pressure might look like. So let's get oriented here. Notice this is midnight essentially, and through the morning hours, afternoon, and back to midnight again. Over here we have the speed, and on the right-hand side, pressure and temperature. So the bottom line here is the freezer temperature. In this case, we're trying to maintain about -5 degrees. This line here represents the degrees Fahrenheit of float. So notice if it's 0 right here, we're not adjusting the suction temperature up at all, but at sometimes, notice here, we're getting as much as 2 to 3 degrees, or even close to 4 degrees of float. This would be setting the suction pressure set point up, coming to the compressor. This next line, the squiggly line here, is the actual suction pressure. So instead of temperature, now we're looking at pressure. Notice it's right around 5 pounds per square inch. And these little squiggly lines that occur periodically, those are defrost cycles that are occurring. And the top line here is fan speed. And notice this one is set at 70% speed in this application. This is real data from an actual site. 70% fan speed was selected as the slowest speed that they wanted to go at. So let's take a moment in time here where the temperature in the space went above the set point, and notice we are resetting the suction temperature down to regain temperature. And so we're floating the suction pressure down. We can see that pressure actually coming down here. And then what we get below or at the set point floated up. And so we're kind of bouncing up and down with 1 degree or so of float occurring here. Notice temperature went below the set point. Float started occurring again. And then we're above the set point, so the float coming down, no float. And we're still above the temperature, say right here, with the 0 float, so then we start speeding the fan up. Notice we regained temperature a bit, but then lost it again above the set point. No float, fan went up to 100% speed. And so this may be when a shipment arrived, the dock doors were opened, temperatures were going up. So notice at this point here, full fan speed, no floating of the suction, but then recovery occurred, temperature back down below the set point. So the fans go back to the lowest speed, and then notice here starting floating the suction pressure again. And if we take the course of a day here, notice with 0 float here, we're floating on an average a couple of degrees. So there's a few % energy savings there. And then, of course, all this fan savings occurring most of the day. So interesting application of
David?
both. Yes.
David,
Hi,
I have
Beth.
a question. Hi, I have a question that Tom would like to ask you about suction pressure. I'm going to unmute him so he can ask the question. Go ahead, David. Tom.
Yes, I'm wondering, when you talk about increasing the suction pressure, we talked about the maximum efficiency being that you're going to use all the liquid refrigerant in the line, and evaporate it. Won't that result in unused liquid refrigerant being in the line by increasing the pressure?
Well, okay, good question. So let's see. I'm going to click back to a diagram. So we don't want to feed any more liquid in here than is going to be evaporated. Now, most expansion valves here would just have a temperature sensor or pressure sensor here to regulate that flow. In larger industrial systems, sometimes we just flood the evaporator with liquid, and there's a recirculating tank here that just keeps the liquid in the evaporator and not going to the compressor. So when we talk about resetting the suction pressure here, it's essentially causing the compressor to unload sooner than keeping the compressor loaded essentially down to whatever temperature that we desire. So when we talk about suction temperature or pressure reset at this point here, it's just affecting how the compressor is loading. If the compressor is loading with a slide valve, then it's just going to actuate the slide valve at a higher temperature than a lower temperature. If it's variable speed on the compressor, then it would just slow the compressor down. And that's where we get the energy savings. So if I'm addressing your question correctly, then no, we don't want any liquid coming back to the compressor, and the set point of unloading the compressor should be independent of any liquid return.
Okay, thanks.
Did that get it, Tom?
Yeah.
Okay, good. That always concerned me as well. So so if we're looking at this set, the adjustment of that set point is just a constant attempt to get up to a higher temperature and resulting pressure, which then reduces the compression ratio and attain the savings. Also wanted to put this one slide in here to draw your attention to the efficiency of evaporator coils. I'm going to click back a second here, and we'll just to the evaporators. We're talking about this device right here. So we got the fan, the coil. So, the question is, how much horsepower does it take from this fan motor here to draw the air successfully over this coil? Now, some coils have very compact fins. They get a lot of surface area, but it takes a lot of horsepower to draw the air over the coil. And this is what we sometimes refer to as the specific efficiency of the evaporator. So it doesn't have anything to do with the compressor. It's just how much horsepower does the fan take to overcome the pressure drop across the coil. So in our slide here, we've got about 400 evaporators. Each little dot there represents an evaporator out of the catalog. And we're getting BTUs of heat transfer per fan watt. So notice a really efficient low-temperature coil could convey, say, 60 BTUs per fan watt, where an inefficient one might only convey 20 BTUs. So this would take 3 times more fan energy to get the air across the coil as this one. And then also with the medium temperature coils, we can see a similar behavior. These would be considered efficient coils, then everything down at the bottom on medium or low temp here, inefficient coils. And this specific efficiency is not in the catalogs. This is something where you have to take the data from the catalog, do the math, and come up with a number. So not all evaporators are created equal. Some of them are real dogs, as you can see on this chart. Okay, so the last thing we wanted to address here was the compressor itself. So we've got the variable speed drive in this cabinet for changing motor speed, and then here's the slide valve. So let's take a closer look at the slide valve. When the slide valve is actuated, it opens up and lets refrigerant gas avoid full compression going through the rotors. It lets some of that gas go back right around to the suction. As a result, what comes out the discharge is some fraction of the full quantity of gas that could go through those rotors. So we could have half of the refrigerant just being released right back to the suction and half going through the full length of the rotors. This is an adjustable amount here, and we can unload this compressor rather than turning it on and off. We can just allow any percentage of the gas back around to the suction. An alternative to that would just change the speed of these rotors. So instead of just allowing the gas to return to the suction, slowing the rotors down achieves the same reduction in flow rate or mass flow. However, the reduction in speed reduces the friction that's occurring of the rotors against the other rotor and against the housing in the compressor, thus giving us an additional benefit over the slide valve unloading method. So this next slide here showing capacity along the bottom of a typical screw compressor. I think the name's been removed here, but this is relatively typical. And the percent power in input, brake horsepower. And what's interesting to note that if, let's say we're at 50% load on the slide valve at plus 40 degrees, we're at about 55% power to deliver 50% of the mass flow. Not so bad. But if we're down at minus 40 degrees, notice it still takes approximately 75% of the power to deliver 50% of the mass flow. So pretty severe penalty of using the slide valve in a low temperature application, which when we compare the performance to variable speed, we get more savings for our variable speed in the low temp than we do in the medium temp. Let's take a look at a couple typical compressor performance curves. So these are screw compressors with slide valve, variable frequency drive. Here we're at minus 25 degrees, single stage, 125 horsepower compressor. And so we've got two curves on here representing compressor power or pumping, and we're expressing that in pounds of refrigerant per motor kW. So the more refrigerant compressed per kW, the more efficient it is. So notice this 3,500 RPM with slide valve control, performance looks something like that. If we have variable speed down to 50% flow and then slide valve below that, so the area under the curve or between these two curves is a savings, and that's expressed with this line right here, improve efficiency. So notice at about 50 or 40% flow, we're seeing about 20% energy savings of variable speed versus slide valve. So this is a low temperature. If we go colder yet, so here we're down at minus 35 degrees as a booster or low temperature compressor. This is on ammonia 717. This is very pronounced here where notice from 50% up to fully loaded, the efficiency of the compressor is almost even over that whole range. And then we start using the slide valve after 50% speed reduction because some screw compressors won't operate very well below 50% speed, begin to experience some blowback of refrigerant. So here's a slide valve performance, variable speed. So you notice even here at 50% load, we're seeing almost 50% energy savings of slide valve versus variable speed. Very interesting application here. So there we have it. Some good energy savings can be attained. Generally, if there's a lineup of compressors, say there's 3 or 4 low temperature compressors and 3 or 4 medium temp, Maybe variable speed is used on just one of the compressors as your trim compressor, and use the other ones either across the line, pretty much fully loaded, and then use the variable speed as the trim. Some put variable speed drives on more than one compressor, although I think most of the benefits can be achieved from just having variable speed on one compressor at that temperature lineup. Okay, so I guess that's the end of the slides. If we have any other questions, well, we have a few minutes left. Beth, do you want to hand it back to you, and we'll see where we go.
Thanks, David. Before we get to the question and answers period, I wanted to remind you of some upcoming webinars and seminars that we have, and you can visit our website at energyeducationcenter.com to find out more. David will be teaching the last three here on the screen in front of you, owning and operating efficient motors, variable frequency drives, and air handling systems in May in Wilsonville. So if you'd like to meet David live, feel free to register for those. Within a few days, we'll be sending you a follow-up email with a recording of this session and a PDF of the materials. And at this moment, I'd like to draw everyone's attention to a feedback survey, which I'm going to open here. It should just have appeared in the bottom right-hand corner of your screen. Please take a few moments to complete the survey. During Q&A, we really appreciate your feedback and do use it to improve future webinars. And now, if anybody has any additional questions, you can continue to submit them to me through chat, but I'd like to go ahead and ask the first question that I've received here, which is, David, why is head pressure so important? What is a good low pressure we should shoot for?
Yeah, so we need to get the refrigerant compressed, or when we compress refrigerant, it gets hotter. The temperature rises, and we desire that to get the refrigerant hotter than the ambient. If the condenser was 85 degrees and the ambient was 85 degrees, no heat would transfer out of the condenser. So to get the heat outside, the refrigerant has to get hotter than the ambient. So then the question becomes, how much hotter? Of course, if you're 1 degree above the ambient, so say the ambient is 85 and the refrigerant is 86, not a lot of heat is going to transfer because the temperature difference isn't very much. And now the question becomes, what's the size of the condenser versus that temperature difference? It's the surface area of the condenser versus ambient. And generally, we're worried about the hottest day. So let's say we get the hottest day, then how big does the condenser need to be, and how high of a temperature does it need to be to get the heat to go outside? So usually equipment is selected to attain that worst case scenario. And quite often, condensing temperatures happen 10, 15, 20, or even 30 degrees above the ambient. So if it's a 100-degree day, the refrigerant might condense at 130 degrees. And a lot of the catalog equipment actually strive to make the condenser as small as they can to be competitive, because that's the metal. We're talking about tubes and fins and outdoor coils, so to minimize first cost, they'll run very high temperature condensing, and as such, high pressure, that affects the compression ratio, and you may need that for the hottest day. This floating head pressure, on the other hand, says that on milder days, when it's not so cold outside, instead of having a fixed pressure condensing control, let's adjust that pressure set point down to something you can attain on a milder day, still get the heat transferred, but do it at a much lower pressure and temperature. And that's what the floating head pressure allows us to do, and there's those great savings and benefits. But many systems just run at fixed head pressure, and yes, you do save at the fan if you shut the fan off, but there's more savings available at the compressor, sometimes as much as 4 or 5 times more savings at the compressor than you'd have at the fan.
Great.
Hope that answers that one.
Thanks, David. One more question here. How efficient is evaporator fan cycling compared to evaporator fan VFDs?
Well, in most cases, evaporator fan cycling would, as far as the fan motor itself, would be fairly close to variable speed in terms of opportunity for kilowatt hours saved. The disadvantage, though, of fan cycling is a somewhat erratic temperature control. So fan off, temperature goes up, fan on, temperature goes down. Some products are not so amenable to that wide swing, but whenever there's on-off control, it basically necessitates a deadband, or that temperature at which the fan goes on and off, and that deadband could be, say, 10 degrees. So on, off, and then you live with that temperature difference. And in variable speed, we can usually maintain a much closer temperature set point and run the fan at that partial speed and not have to handle that change in temperature. So in terms of kilowatt-hour savings at the fan, you might even come close to a breaking even between cycling and variable speed. However, the variable speed helps us maintain a more steady temperature.
Great. Thanks, David. I think we have time for one more question, and that is, how important is a central control system in an efficient facility as opposed to using local controls on compressors?
Yeah, okay, good one. Sometimes we might categorize industrial refrigeration as having just local controls. So that would be a controller just for, say, fan, evaporator fan, condenser fan would be separate controls, compressor controls, those that come with the compressor. The next level up would be distributed programmable logic controllers, and there could be many of them within a facility. So we're adding a microprocessor controller that would operate fan speeds, control temperatures, but not necessarily networked together. Those would be just microprocessor-based distributed controls. And then ultimately would be a control system that networks all of the various subsystems together to a central location where systems can be monitored and more advanced strategies could be applied. So these floating suction, floating head pressures can be attained at the local loop, but a desirable outcome in most cases is to continue pursuing either distributed programmable logic controlling and then ultimately networking those together into an energy management system for the whole refrigeration systems. So we can get some of the savings out of the local controls, but ultimately having all of this data available at a central location for data logging and trending, continuous commissioning, and that's the greatest advantage of the centralized control.
Great. Thanks, Tom. And I'd like to thank all of you for joining us today. That was our last question. We'll stay online for a while in case any of you would like to ask any additional questions through chat. But thank you again, and we hope to see you at a future webinar.